Okay, my personal words to Spenta I have said, so I will now go to the physics, and as I said during the banquet, Spenta had a very interesting work on a model which was just a matrix model, and actually turned out to have not just a beautiful structure, but very strong implications. And it was related to a deep problem trying to understand how confinement works. So I will try to bring to Spenta another toy model and work done in collaboration with Jose Barbon. And I'll try to also say words on the big picture, but also describe the toy model, and it's not going to be a one-plaquette model, it's going to be a full quantum mechanical model. The issue which we are going to discuss are various aspects of singularities, which Rajesh assured me that interest you, Spenta, so I will look at that. Now, as credit, and sometimes, as I said, people are interested in it, I want to share with you a solution to the problem of credit, which was suggested by Chagall. And I learned that actually by looking at the opera, the ceiling of the opera house in Paris, where Chagall painted many operas and many composers, but there are some which either there was not place for or intentionally he didn't want to put in there. So he wrote this, he gave them a bouquet of flowers and suggested that they excuse him. So I think from now on we can use this anytime we want to be sure that everybody is happy with our references. Okay, so now let's go to the problem of singularities. So one question is, what do singularities reflect? Now usually what singularities reflect is that we don't know enough about the problem. When we went from classical physics to quantum mechanics, it was driven by a singularity, and we had to change the rules of the game. In recent years, things have not been so dramatically. Usually we found out we missed some degrees of freedom. We either didn't realize they're there, or we integrated them out in an incorrect way, and that was the source of the singularities. Now, general relativity is different in that sense, that they have in them horizons, and under the skirt of the horizon, maybe you can hide various types of the singularities. And it's really a question, is there a different resolution in general relativity to singularities, or is it just each time our ignorance, we have to add some input and then things will become okay? Now, string theory has many time-like singularities which have been resolved, so I'm going to emphasize here the space-like singularities. So can one live with singularities? Are there situations where singularities heal? And what can one learn from them? You can also ask a question, are they simple or complicated? And here I'm just telling you, Spenta, they can be, some are very simple, but I'm not going to discuss complexity today. So again, in a typical way, I heard Spenta sometimes ask, what are you actually trying to say? So I'll say what I'm trying to say here. So what we are trying to describe here, there will be two different boundary theories in the context of an ADS-CFT. The bulk will contain a singularity on a semi-classical level. The two boundary theories, one will explicitly demonstrate a singularity, while the other will not. And the question is, how can we learn, what can we learn from that? And in particular, by doing a D=1 model, toy model at this stage, with hope that it's more than a toy, one can actually see in detail, in full, and analyze the problem in full. So that's what we are trying to say. So here is the model, and I'm teaching for the students here. I'm just take something which, even if you take just this out of the talk, I think it's worthwhile. So in general, as you know, if you have a quantum mechanical problem where the potential is p²/2n plus lambda x to the n, this model has no coupling. You cannot expand in large M, and you cannot expand in lambda. And the reason is that you can always rescale the problem so that you have a model where the whole lambda and M dependence is extracted in the energy scale, which you're familiar with a harmonic oscillator with the h bar omega, and then you are multiplying this by two operators, both of them non-compact, which have equal weight, and therefore you have no way to do a perturbation theory. And I heard this first from in a lecture, pedagogical lecture by Ed Witten many years ago. And he used this to explain several things. One, where does one have a real parameter to expand? And that's the large N. And he did this. He showed a model which is take the problem of a hydrogen atom, don't change the potential, but change the number of dimensions, keeping the 1/r potential, even though it's not the electric potential in higher dimensions. And then you find out that N is a real parameter. The particle obtains an infinite mass, and if you wish, the problem has a master field, which is a classical configuration where the minimum of the new effective potential, which contains the measure, came in. And this is actually a nice example of a master field which reflects a quantum mechanical problem, but you succeeded to reduce it to a classical problem. Of course, it doesn't give the Rydberg energy exactly, and anyhow, you know that the energy scale is there, so if you put 3, you're not going to miss by much, but not by little as well. So this is a result of that. However, if you do this exercise, you will find that there is one case where this doesn't work. And this is the case when this power is -2. In the case when the power is -2, the idea of taking out the energy scale doesn't work, and you actually get here an example of conformal quantum mechanics. This was done, I was first aware by work of Alfaro, Fubini, and Alfaro. Now, this model is going to serve as the bare construct for our toy model. Things are going to be added to it, but it's going to be a limiting model, as we will see. Now, the general context for the big picture I want to put it in is that one of the things which kept me attracted many years and still to string theory is there is a lot of magic in it, and the magic is not yet explained. And one magic is that no concept in mathematics remains unambiguous. So you think the metric is well defined, you know that under certain circumstances you can describe all the scattering amplitudes in a world which has one dimension, which is a circle, by explaining that it's a radius r and a radius 1/r. All territorial disputes could have been easily solved if you accepted that as the correct. Topology. We have examples of theories where the target space can be a sphere or can be a torus, and everything you can calculate is the same, so you cannot tell what it is. Then we know about the number of dimensions. We know that we have examples where 1 equals 3 and where 4 equals 10. We know in general that when we write down Wess-Zumino-Witten models, we can write them either on a group whose dimension is G, and the target space has dimension G, or you can write them on their Cartan subtorus if their level is 1, and that would be the rank of the group. In general, the dimension is larger than the rank, so you have two different narratives with totally different dimensions. You know the same about ADS-CFT. With one set of degrees of freedom, you can describe the problem as 4-dimensional. With another set of degrees of freedom, you can describe it as 10-dimensional. You know that there are time-like singularities in string theory, like the orbicircle, which actually, for a certain radius, is equal to a circle with a certain radius. So again, you have two different narratives, one with a singularity, one without. You know that non-commutative theories can also be described by a set of different degrees of freedom, as if living on a commutative manifold. The same goes for associativity. So actually, I don't know of any concept in mathematics where there isn't an example in string theory that you can describe it in different ways. And I don't know of the unified picture. I think that's one of the challenges. We do it case by case, we don't have a unified picture. I want to add to this a situation. This is my dream of relaxing. Maybe some of you also would like to relax at least for a week at such a place. So assume that you are relaxing infinite amount of time at that place. And I contrast it with the picture of Goya where Cronus eats his son. So you have a situation where you have a big crunch, which is a singularity in the bulk, to which you can give an alternative picture of being in nirvana for as long as you want and nothing happens. And I would like to go a little bit into the guts of that. So this comes in, or can be phrased also in a different way. Presume that we have some global parameterization of ADS. We can write it in one way, and here is one global metric, and we can go to its conformal boundary and have the Einstein parameterization of that. Then we can take a de Sitter parameterization of that by having de Sitter slices, and when we go to infinity, we have a one-dimension reduced de Sitter picture on the boundary. What does this mean? In one case, in the de Sitter case, we cover only the orange part. On the other hand, in what I'll call the Einstein case, we cover the full green part. So this poses supposedly a question to ADS CFT. This theory and this theory on the boundary will have some relation between them because they are both boundaries of ADS, but they seem to describe different bulks. So how can you do that? Is there a contradiction here, or is actually all the information already sitting inside? Now, there is a transformation, which is the one which I will use time and again, which relates the two, and that's a Weil transformation, which has the following form. So it relates both the Einstein and the de Sitter manifolds on the boundary. Now, the way one looks at it usually in the bulk is one says the following. All the information is sitting there. If you want to know how to propagate, the important point is that you have one common time slice of both parameterizations. And then in what Lenny called pull back, push forward, or some other combination, you say you go back with the Hamiltonian, which serves you, let's say, in de Sitter coordinates. And then if you want to evolve your state, just evolve it with a different Hamiltonian, the one of the Einstein. And therefore, you will be able to go all the way. So as long as you have a common T-slice, there is no problem, and you actually can evolve everything. And both these things are related to what we are going to do as we go on. So now, the parameterizations that I used both actually here had boundaries. And one question, are these boundaries just general coordinate transformation boundaries, or are they real? So in some cases, one definitely can continue, and of course, the anti-de Sitter case is the one where you can easily consider continue through that. The other cases where it's more complicated, I don't have time to enter into all how one analyzes that here. We'll just do a little in the quantum mechanical case, but let's challenge the system by asking it, okay, how does this story look when inside you have a big crunch? And in general, if you have an OD, one scalar field together in the bulk with ADS, the generic situation is a crunch will occur. And there will be two different boundaries one will be able to have. And the question is, what does it teach us about the physics inside? So in particular, we are going to have one parameterization, which is the Einstein parameterization, it will come up, and the other is the de Sitter parameterization. In one, the time parameter goes from -infinity to +infinity and covers the whole region. In the other, there is a block which was imposed by the coordinates that one has chosen. Now, in the cases that one is going to study are cases when the singularity reaches the boundary in a finite time. Now, that's a big asset relative to black holes, because in such a situation, you can, or you have a hope, which afterwards is borne out, to be able to describe the system by boundary operators which are local and which can be classified by being relevant and marginal. So this is how one actually engineers big crunch singularities. One goes to boundary series, one adds to the marginal and relevant operators, and this is a way to describe on the boundary what happens in the singularity. Now again, I will just give a glimpse, and I will show it exactly in the quantum mechanical case. One way to do it, you take the theory and write a Landau, try to get a Landau-Ginzburg picture of it. How do you do that? You concentrate everything in a brane which moves from inside, where the bad stuff is happening, to and through the ADS outside. And you write the Born-Infeld equation of that object, and then you look at where you are, and you relate that to some operator, I call it here a mass, which would be some relevant operator on the boundary. And this will be related to some expectation value of the system on the boundary. And the nearer you approach to the boundary, the better this description becomes. You shouldn't be going too fast. And in that situation, you can actually map up what is a theory you will get on the boundary. And this was used many years ago in ADS3, and here it's used for description of bubbles which are concentrated around the motion of one brane. I will show in the quantum mechanical example exactly what it is. So again, from the general point of view, of course, the good thing in the boundary is that some people say it's the only definition of the theory, but definitely it's the non-perturbative definition of the theory. And there are several cases in general. One would be you have a CFT with a relevant operator with a positive sign. Such a theory in the bulk is going to lead to a gap. You're going to have a bubble of nothing. You're just going to, the depletion of degrees of freedom, which occurs here in the infrared, makes the depletion of space in the ultraviolet of the theory in the bulk. Then you have a case like here, where you have, by adding a negative sign relevant operator, you have a new minimum. This new minimum can be a trivial vacuum where nothing survives, and in that case I have nothing to say. But if this theory also has many degrees of freedom, then this is a theory which will reflect the big crunch inside the bulk. Now, there is also situations, and that's how these studies actually started, when you get, I'll call it here, it's permitted garbage on the boundary, and the garbage on the boundary reflects garbage in the bulk, but that's permitted garbage, because you find out that in the bulk, what you have is at a given Cauchy slice an infinite amount of energy. And of course, in such situation, you should crunch. So when the theory is ill-defined on the boundary, it's also ill-defined, at least in the example studied, in the bulk, so no great deal. Now, if the boundary theory is well-defined, then in principle, so is the crunch. As this is the non-perturbative description, that means, in a way, the singularity has been resolved, and we will discuss that. Okay, now, one can look at the situation that I described now. In that situation, we are sitting on a de Sitter on the boundary. That de Sitter contains no gravity. It's just your world volume which expands. Your coupling constants are not time dependent, and consider the situation where you add some relevant operator. As I said, if that relevant operator has a positive sign, you have an IR gap, the theory contains nothing, and you have a hole in the bulk. That's not the case one is interested in. However, when epsilon is negative and you have a non-trivial large N extra minimum, that can give you a picture of a crunch in the bulk. The problem is it's well defined, so it's a surprise, because this is, let's say in the zero, if we take gravitation coupling to zero, this is our world. We have a standard model, there is spontaneous symmetry breaking, and our world volume seems to move de Sitter. Now, there is, if you want to see what happens and you want to see the crunch, you can again do the map into the Einstein frame by doing this vile rescaling. So in the Einstein frame, marginal operators will not change, but relevant operators will obtain a time-dependent coupling. And if epsilon is negative, what you will find out is that the bottom drops up after a finite time. And you have the system in the Einstein frame clearly exposing some drama. So there is always a question, okay, maybe this is because you are in a singular frame. So you have to try and detach the general coordinate problem from the case of the dynamics. And this we discuss in this case as well, but I think it's best to do it in the quantum mechanical case here, because there things can be solved exactly, and you can see exactly what is happening. So we are, for many years, and maybe we still should, we're waiting for the knight with a shining armor on a white horse who is going to save us from the singularities of GR. On the other hand, it may be a simpleton which will do that. Maybe the singularities are dragons, and maybe they are just nice, calm pussycats. Okay, or if you wish in a different way, a person living in the sitter and he sees somebody saying the end of the world is near, you just don't realize that because you are in the wrong coordinates, or that's one possibility. Is he a crackpot, or are we ostriches which don't realize that? And I'm going to discuss that in view of the quantum mechanical example later on. So now let's go to the quantum mechanical case. So here is the general potential on the sitter that I wanted to describe. And let's go now to the case where d equals 1. So as I described before, it will not be a surprise for you that the field phi, which had a positive power, will become now 1 over phi squared. That's what we expected should happen. The surprise is actually with this term. This I didn't know before, because of course there is no curvature at d equal 1. But what I didn't realize is that the coupling also has a singularity. And actually when you go to the limit of d equal 1, you find that this term does survive. And the way it survives depends on if you are on de Sitter, or if you are on an Einstein frame, or if you are in Minkowski space. This gives different values to the number k, which appears in here. In particular, on de Sitter, this, which was a positive thing in higher dimensions, becomes, if you wish, a tachyon. It gets a power of -1/4. So when you do the case of d equal 1, you are going to have this term, and whatever operator you will want to add, and we'll add various operators. I promised to show more explicitly how to derive the boundary potential in the picture of a brane moving by a Born-Infeld action. So here is a probe Brane. This is his action as it approaches towards the boundary, again using the method which was used for ADS-3 many years ago, and doing the identification of the field on the boundary with the point where the brane is, and taking the limit, you end up exactly with the potential I discussed. You have the p squared term, you have the omega k squared phi squared term, and you have the 1 over phi squared term. So you can really derive this as a boundary potential. So we are back here, and we want to look at how this model behaves. So in the case when one has a de Sitter, the omega which will appear as would be a quarter. There is already a minus sign there. In the case of the Einstein frame, it would be -1/4, and in the case of Minkowski, it would be 0. Now what is interesting, and I don't have time to elaborate on it here, but it's interesting that the frequencies omega are related by the Weil rescaling, not just by multiplying by omega squared, but if you wish, there is an anomalous term which is related to the boundary, which does not depend on the omega you're operating on, but depends just on the Weil rescaling you are doing. Okay, so back to this model with no modifications. This model is SL2R invariant. It has commutation operators of the dilation operator, xp plus px. It has the special conformal transformations which are represented by x squared, and they do an have an SL2R algebra. Now, for some reason, unfortunately, Subir left, so I can't ask him, but I'm told that this is not the right model that one should think upon when one does ADS2. Now, I'm told that when one does ADS2, one should go directly to the Schwarzian based on various isometry arguments that the natural extension should have as well a term which is general coordinate invariant, which of course this term is not. It's only invariant under the SL2R group, not the full general coordinate transformations. So it's dismissed for that purpose. How does it look like? Well, it has a positive, for a positive coupling, and actually even for a negative up till -1/4, the spectrum is continuous. The system has no ground state, which is very interesting. And if you wish, you have here an analogy to the Breitenmüller-Friedman bound, because, yes, please. The only request, Andy, can you park the question? Because I see I have 0. So you'll park it and come back? Thank you. And the spectrum, there is no normalizable ground state for that system, and the spectrum is continuous from 0 to infinity. So it's an interesting system. It has no ground state. You can change it by building an elliptic operator. In general, you can take any combination of H, C, and D, and you will find that the spectrum, if you do at C and are elliptic, is actually also SL2R invariant, has a very interesting structure. It looks like an harmonic oscillator. The spectrum is gapped by equal gapping. Now let's deform it by adding some marginal operator. The only thing I want to remind you that in 1 dimensions, all our intuitions change. So what we would think as irrelevant operators mix with relevant operators. And in general, the power delta which would appear here must be smaller than 1 to be relevant, equal 1 marginal, and between 0 and 1, softly relevant. So here are explicitly the examples I discussed about in the general context. If one has delta smaller than -1, this is case A, one has a very strong relevant operator, which we should say has a ADS2 or whatever is there, should have a bubble of nothing in it. On the other hand, there is a possibility with the other type of marginal operator in the region which is mildly, you can get minima. And these minima do contain in them extra stuff. And these are the things which should be related to the crunch. And we will see in what way, how. So for example, if you have 1/phi, which is a soft relevant operator, you just get a hydrogen atom coupled to the conformal quantum mechanics. You can solve it exactly. You have scattering states and you have many bound states. So that's the type of system which is rich enough to be able to contain a crunch inside the bulk. There is, in the pure de Sitter case, actually it's unstable, and this is the case which, I'm sorry, I'll take 5 extra minutes. In this case, we are going to see a healing. This is the example where you don't need to wonder in what coordinates you are. The system can heal itself, which is something I hope that, like Hawking-Page, one day will emerge as a more general mechanism. And I will describe it in a moment. Okay, so these are the classical maps between them, and you can do the quantum maps. Quantum maps tell you exactly how wave functions behave in one frame relative to how they behave in another. So you can see here the difference between the nirvana state and the state which is not nirvana, and you can see how it reflects itself inside the wave function. So let's take the state which is a candidate state for a crunch, that is in the de Sitter frame is stationary, and let's compare it to the de Sitter. So here it is, some wave packet sitting inside the de Sitter space, do the transformation on it. What happens, everything goes very fast into what is the UV of the problem. So you really see the picture of how the problem goes into the UV, and this is what you see of the crunch. You had in the de Sitter stationary, you go to Einstein, everything is rushing into the UV. The opposite, you can do it, you can calculate here exactly energies. You find that the potential energy for the bubble of nothing is positively infinity, On the other hand, for when you have the crunch, it's negatively infinite. The kinetic energy becomes infinite but positive, so you get exactly the state that you would expect. And you get the opposite picture, which I won't show in the other part. So here I want to make a remark which to me is important. Okay, we claim on the one hand that the two systems are the same, and then we show different behavior. So what's going on? So I don't know how, I think that you're also attuned to my talk, that you didn't look every second in your email, so you missed that LIGO just announced that they have discovered that one direction of the universe is a circle. I think most of you missed that. Okay, now we know from duality that R equals 1 over R, right? So has your picture of the universe changed now? Has everything shrunk? Or just do we continue to look at the universe just as we looked before? Okay, what is the reason? So one interpretation for that puzzle, which I give myself, that our brains evolved. We are local objects, most of us, and therefore we really use local operators. So we are built for momentum modes, not winding modes. They're not geared in the way we perceive stuff. So for us, nothing changed. And I would say that here, something similar must happen. In other words, non-local observers, which would go very fast, let's say compared to the Hubble expansion of their world volume, would begin to detect that stuff is going on. So it's not that there is, in one case, Simpson is crazy and in the other is not. It's just you need the non-local observers in order to detect that the two theories are the same. And I think it's interesting to be able to actually turn this intuition into some concrete operators where it's going to happen. I point out also that we have different Hamiltonians, and I think a nice algebraic structure which survives in higher dimension is that the Hamiltonian in the Einstein frame and the de Sitter frame, their commutator gives a dilation operator. So on states which are invariant, there is no problem. Okay, I'm finishing in 1 minute. Now, what happens about the healing? I want to show this case because it came only in the quantum mechanical case. So when we had a situation in de Sitter with a crunch, we had an instability of going to infinity through tunneling. On the other hand, and you should realize that because we're in quantum mechanics, going here to large phi means not reaching the boundary, because the boundary is at phi equals 0. So that would mean in a singularity situation that if the tunneling is fast enough, this piece will not go to the origin and give the very high fluctuations responsible to the crunch, but will succeed to heal itself by breaking away. In higher dimensions, it would mean the singularity won't really reach the boundary, but would reflect back inside. So again, I hope that for some future Hawking-Page transition, this will be important. Okay, so the conclusion is we saw some new aspect. There is apocalyptic eternal duality. The crunch can be seen in the UV, must have non-local aspects, and maybe a detection of some possible healing mechanism without needing to go to different coordinates. Spenta, congratulations. I wish you, on top of everything, many more years of intellectual stimulation and friendship.
Thank you.